Alright, in this video I'll be solving the 9709 Pure Mathematics 3 paper 32 February-March 2025. And before we get into the video, I just want to kindly ask that if you find the videos that we make useful, please subscribe. 81% of the people that watch this channel are not subscribed, and I know it may not mean much to you, but genuinely it goes a long way for me, and it's a reflection for me. It's feedback. People actually like the videos that we're making, so we encourage us to post more and more of this content. So please subscribe. Thank you. Number 1. Solve the equation, the natural logarithm of 1 minus e to the negative 2x plus 3 is equal to 0. Give your answer correct to 4 decimal places. Okay, so for starters, I am going to move this 3 to the other side. Reason being, I want to apply the exponential function on both sides. I could do it like this, but it's easier to think about it conceptually when I move the constant that doesn't have a natural logarithm to the other side. So we'll do that. So ln 1 minus e to the negative 2x is equal to negative 3. And now because we want to get rid of ln, we can just apply the natural logarithm. But what you do on one side, you do on both sides. So this e is the inverse of ln, so it cancels out the ln, and you end up with 1 minus e to the negative 2x, and we've got e to the negative 3 on the other side. And now we want to make x subject of the formula. So I'll move this to that side and I'll move this to that side. So I've got e to the negative 2x is equal to 1 minus e to the negative 3. And now I'm going to take the natural logarithm on both sides to bring down or get rid of this e and therefore bring down the x. So ln, you end up with negative 2x because ln and e cancel out, is equal to ln 1 minus e to the negative 3. And divide both sides by negative 2. You've got that x is equal to negative 1 over 2, the natural logarithm of 1 minus e to the negative 3. And they say they want their answer correct to 4 decimal places. So this is negative 1 over 2 ln 1 minus e to the negative 3, and this gives us 0.0255 correct to 4 decimal places. Number 2, the equation of a curve is xy squared plus ln x plus 2y is equal to 1. Find the gradient of the curve at the point x is equal to 0. So what they're asking me is to evaluate dy dx at x is equal to 0. So to be able to do that, we first need to find our gradient function, which is dy dx, and to do that, we just need to differentiate. And in this case, notice that we've got an implicit function, i.e., we can't easily make y or x subject of the formula. So we're going to differentiate this implicitly. So this is xy squared plus the natural logarithm of x plus 2y. And this is equal to the derivative of 1. So if you differentiate xy squared, this is a product. So first hold the x, differentiate y squared. You differentiate y squared, you're going to get 2y dy dx. Now hold the y squared and differentiate the x. You differentiate x, you get 1. Plus, now we move on to this term. This is the natural logarithm of x plus 2y. So it's 1 over the bracket, which is x plus 2y, multiplied by differentiate the inner function. So differentiate the bracket. If you differentiate x, you get 1. If you differentiate 2y, you get 2 dy dx. So plus 2 dy dx. And this is all equal to, if you differentiate a constant with respect to x, you get 0. So here we've got 2xy dy dx. And then here we've got, that is what? Plus 1 plus 2 dy dx all over x plus 2y plus this y squared is equal to 0. So I'm going to multiply through by x plus 2y to get rid of this denominator. So that's 2xy multiplied by the x plus 2y dy dx. And here that just gets rid of our denominator. So plus 1 plus 2 dy dx. And then we've got plus y squared, and it's being multiplied by the x plus 2y. This is all equal to 0. And now I'm debating on whether to expand this or not. I think I'll expand that. So 2xy times x, this becomes 2x squared y. 2xy times 2y, that's 4xy squared. And this is all multiplying our dy dx. I want to move everything that doesn't have dy dx to the other side and then keep everything with dy dx on the left. So plus 2 dy dx. And this is equal to, we've got the 1, so negative 1. And then we've got this, that's negative y squared times, in fact, we can expand that. So negative y squared x, xy squared, and then y squared times 2y, so negative 2y cubed. Okay. And now we can just factor out dy dx on the left, dy dx. And so here we've got 2x squared y plus 4x y squared plus the 2. And this is all equal to our negative 1 negative xy squared negative 2y cubed. And so we have that dy dx is equal to, that's negative 1 negative xy squared minus 2y cubed all over, that's 2x squared y plus 4xy squared plus 2. This is our dy dx, this is our gradient function, and we need to evaluate this when x is 0. But there's a problem because we also need to know what y is. So to find what y is, we can just substitute into the original equation, right? Our original equation is x. Let me put that in red because it's a side quest. Our original equation is xy squared plus ln x plus 2y is equal to 1. When x is 0, this becomes 0 times y squared. Then we've got plus ln 0 plus 2y is equal to 1. So we have that ln 2y is equal to 1. Apply the exponential function on both sides. You have 2y is equal to e to the 1. And so you've got y is e over 2. Okay. So we now know that when x is 0, y is e over 2. And so we can use that information and substitute here to get our gradient when x is 0. So we're saying dy dx, and we want to evaluate this at the point with coordinates 0, e over 2. This is equal to negative 1, negative, this part is being multiplied by 0, so it's going to fall away. Then we've got negative 2 times y cubed, so e over 2 cubed, and this is all over. This is an x is 0, so it falls away. This is an x is 0, so it falls away. And this is all divided by 2. So our dy dx here, can we simplify that? On the numerator, we've got negative 1, negative 2, and that's e cubed over 2 cubed. So e cubed over 2 cubed, 2 cubed is 8, and this is still all over 2, and this is equal to negative 1. We've got negative 2 over 8, which is negative a quarter, e cubed all over 2, and then now I'm just gonna distribute the 2, so negative 1 over 2, negative a quarter, e cubed over 2, which is negative 1 over 2, negative 1 over 8, e cubed. So that will be our final answer. The gradient at x is equal to 0 is equal to that. Number 3. The shaded region on the Argand diagram shows points representing complex numbers z defined by two inequalities. The shaded region is bounded by a circle and a line parallel to the real axis. The boundaries of the region are included in the shaded region. Part A. Find two inequalities of z that define the shaded region. Okay, so the shaded region is bounded by a circle. So hopefully you should know when we're dealing with Argand diagrams, a circle is of the form z minus whatever your complex number is. And since we want the region inside the circle, it's going to be less than or equal to some radius. Or equal to, because we're going to include the radius. Sorry, we're going to include the circumference. They mentioned in their last line, the boundaries of the region are included in the shaded region. So we have to say or equal to. If this part was shaded, was dashed, not shaded, then we would have just strictly less than, no or equal to part. So now we need to figure out what this complex number is. That complex number is just the center of your circle, right? So that's z minus, our center has the coordinates negative 2 in the real axis, and then plus I. And then, okay, I didn't give the radius. So from the diagram, we know that this point, okay, that center is atrocious, but we know that this point, if you had to continue drawing along, this point there is at 1. So our radius has to be this distance between negative 2 and 1. There are 3 units between that. So that's going to be less than or equal to 3. So we're saying a circle centered at the complex number negative 2 plus I with the radius of 3. So that gives us this circle here. Now we need to figure out how to represent this line part, because we don't want everything inside the circle. We want everything inside the circle that is below that line. So that line is a horizontal line. So that's going to be a specific imaginary part or imaginary number. We're saying the imaginary number here has to be equal to negative I, because at this point, this whole line is defined by imaginary z is equal to I. So we're saying we want to take less than or equal to negative I. So the equation of this line here is the imaginary part of z is negative 1 or negative I. Maybe just use negative 1 to be precise. So this line is the imaginary part of z is equal to negative I or negative 1. And so we're saying we want all the z values that are inside the circle but below the imaginary part of z being equal to negative 1. Below this line with imaginary part of z is negative 1. Those would be your two inequalities. It's interesting because now this time they've asked the Argand diagram question in reverse. Typically what they would do is to ask you to, they'd give you these two inequalities and ask you to produce the Argand diagram. But this time they've given it in reverse. Part B says, find the greatest value of mod z, the modulus of z, for points in this region. Okay, so we want greatest value of mod z. So we want the greatest distance from the origin to points in this region. So the greatest distance is going to come from that point there, right? So we need to find the length of that line because that's the greatest mod z. And for us to do that, we need to know what the coordinates are at this point. We do know one of the coordinates, which is the imaginary part. We know that that's negative I or negative 1. So if we are to just go back to real numbers for a second, we know that a circle can be written in the form x minus a squared plus y minus b squared is equal to r squared. We can use this idea to help us figure out what the real part of this point is. What's the value on the real axis, right? So with that in mind, we know that the center of our circle has coordinates. It's got negative 2i, so negative 2, 1. And then we know that the y value of the point that we're interested in there is y is minus 1 or minus I, right? So I can substitute into this. So I know that this is x minus the x coordinate of the center minus 2, so that becomes x plus 2 squared plus y minus the y coordinate of the center, which is 1 squared is equal to our radius. Our radius of the circle we said is 3, so it's equal to 3 squared. Now we want to figure out what x is when y is negative 1, because that's the real part or the real value of this point. So we've got x plus 2 squared plus negative 1 squared is equal to 3 squared is 9. And so we have that x plus 2 squared plus that's 2 squared, which is 4 equals 9. X plus 2 squared is equal to 9 minus 4, which is 5. Take the square root on both sides. X plus 2 is plus or minus root 5. Subtract 2 from both sides. X is equal to negative 2 plus or minus root 5. But here, the reason we get two answers is because one of the answers will be for this point of intersection and the other one is for the one that we're interested in. So hopefully you can see that from here we have to take the negative 2 negative root 5 solution as our x value. So our x here is negative 2 negative root 5. So this means that the real part at this point, the real part of z at this point is equal to negative 2 negative root 5. And our imaginary part is negative 1. And so now that we know that, we really can just use Pythagoras. Because if we redraw this, where this is the origin and this is the point that we're interested in, it means that the distance here, that's just the distance in the imaginary axis. That's this part, which is just negative 1. But if we're looking at like distance or measurements, then we can take that as a positive 1. And then the real z, the real part of z there, will be this distance, negative 2 negative root 5. That's this distance there, negative 2 negative root 5. And again, if we're looking at it as a measurement, we can just take this as 2 plus root 5. So plus 2 plus root 5. And then we can use Pythagoras to find the distance of that. Right, so it's going to be, Pythagoras says if this is c, or actually let me write that, if this is mod z, Pythagoras say that mod z squared has to be equal to this side squared plus that side squared. So 2 plus root 5 squared plus the 1 squared. And then take the square root on both sides. Mod z is the square root of your 2 plus root 5 squared plus 1 squared. And In this case, they have not specified if they want this as an exact value or not. So I will punch this into my calculator and get that this is the square root of 2 plus root 5 squared plus 1 squared, which gives me 4.35, correct to 3 significant figures. So that's number 3 done. Number 4, by first expressing the equation tan x minus 60 degrees is equal to 2 cot x as a quadratic equation in tan x, solve the equation for x is between 0 degrees and 180 degrees. So make sure your calculator is in degrees, and now we need to first convert this to a quadratic equation in tan. So the first thing that I'm going to do is to change this cot x using the identity cot x is identical to 1 over tan x. So we have that tan x minus 60 degrees is equal to 2 over tan x, and hopefully you should know that. And now what we're going to do is to use a compound angle formula for tan, which says tan A minus B is equal to tan A minus tan B over 1 minus 1 plus, be careful with the signs, 1 plus tan A tan B. This formula is in the MF19. So in this case, our x will be the A and our 60 degrees is the B. So it ends up being tan x minus tan 60 degrees. And this is all over 1 plus tan x tan 60 degrees is equal to 2 over tan x. And if you punch tan 60 degrees into your calculator, this should give you an exact value. And indeed it does. It gives us root 3. So wherever there's a tan 60, replace with root 3. So tan x minus root 3, 1 plus root 3 times tan x. And this is all equal to 2 over tan x. Now we can cross multiply. So we've got tan x multiplying the tan x minus root 3. And this is equal to 2 times 1 plus root 3 tan x. Expand the brackets, so tan x times tan squared x. Tan x times negative root 3 tan x is equal to 2 times 1, that's 2, plus 2 times root 3 tan x, that's 2 root 3 tan x. And let's put everything on one side, so I'll move the right to the left. Tan squared x minus our root 3 tan x, and we've got minus 2 root 3 tan x. And then the 2 becomes negative, so negative 2 is equal to 0. And we can simplify like terms, so we've got tan squared x, we've got negative root 3 tan x, negative 2 root 3. So that's negative 2, negative 1, which is negative 3 root 3 tan x, minus 2 is equal to 0. So now we've got a quadratic equation in tan x. So we can solve this using the quadratic formula. So in our case, A is the coefficient on tan squared, which is 1. B is the coefficient on tan x, which is negative 3 root 3. C is the constant. And so tan x is equal to negative b, so 3 root 3, plus minus the square root of your b squared, so 3 root 3 squared, minus 4ac. And this is all over 2 times 1. Punch this into your calculator. That is 3 root 3 minus root 3 root 3, and this is squared, minus 4 times 1 times negative 2 over 2 times 1. And this gives us negative root 35. So it's giving me plus 3 root 3 over 2. And the other solution is tan x is equal to, oh, they've written it in reverse. Okay, that's why it looks weird. Root 35 plus 3 root 3 over 2. And so now we have these two equations that we need to solve. So x is equal to arctan of, that's negative root 35 plus 3 root 3 over 2. And so x is equal to, punch that into the calculator, arctan of negative root 35 plus 3 root 3 over 2. And this gives negative 19.797. And this is also known as our principal value. So we can use this beautiful formula PV plus 180N to get our solutions that are within the given interval. So n is an integer, so you can substitute n is 1, n is 2, and so on until you found all the values in your interval. In this case, we only need n is 1 because you find that n is 2 is already too big, it's already beyond 180. So if we do PV plus 180 times 1, we get 160.2 degrees. All right. And so this would be the only solution from this equation, here. You can try n is 2, you see that you should get a value outside of your interval. Okay, so now let's solve this equation. So x is arctan of root 35 plus 3 root 3 over 2. And so we have that x is equal to, punch that into the calculator, arctan of root 35 plus 3 root 3 over 2. And this gives us 79.8 degrees, which is within our interval of 0 to 180. So that will be the only solution from there. You can use the formula again to check if there are other solutions within this interval, but you find that the next one is just going to be 79.8 plus 180 degrees, which is bigger than what our interval has given us, right? So we can conclude that therefore x is either the 79.8 degrees or the 160.2 degrees. And that is our final answer. Number 5. The square roots of negative 4 plus 6 root 5i can be expressed in the Cartesian form x plus iy, where x and y are real and exact. By first forming a quadratic equation in x or y, find the square roots of negative 4 plus 6 root 5i in exact Cartesian form. Okay, so the square roots of a complex number can be expressed in the form x plus iy, as they have mentioned, right? So we're going to use this to help us to find what x and y are, and therefore the square root. What we can do is to start off by squaring both sides. If you square the left-hand side, it gets rid of the square root sign, so we've just got negative 4 plus 6 root 5i. If you square the right-hand side, we've got x plus iy squared. And we want to expand our right-hand side, so that's x squared, then 2 times x times iy, plus 2xy I, and then the last term squared, so plus I squared or y squared. Be careful with how you distribute your powers. if you've got iy squared, this is I squared y squared. And while we're at this, you should know that I squared is equal to -1. So I can just remove this here and write negative y squared, because that's -1 times y squared. Okay. So if we rewrite this, we have that -4 plus 6 root 5i is equal to x squared. Want to put the real parts together, minus y squared plus 2xyi. So we know that two complex numbers are equal if and only if the real parts are equal and the imaginary parts are equal, right? So if this real part is equal to that real part and this imaginary part is equal to that imaginary part, then we say that our two complex numbers are equal. So based on that, we can say that -4 has to be equal to x squared minus y squared, and 6 root 5 has to be equal to 2xy. And we can use these two equations, solve them simultaneously, and get x and y. So let's make x the subject of the formula here. That becomes 6 root 5 over 2y. And so you've got x is equal to 3 root 5 over y. And if we substitute it back in here, that's -4 is equal to x. That's 3 root 5 over y. And this is squared minus y squared. Let's expand. -4 is equal to 3 root 5 squared. So square the 3, that's 9. Square the root 5, that's 5. So 9 times 5 over y squared minus y squared. And so if we simplify, -4 is equal to 9 times 5, that's 45 over y squared minus y squared. And now let's get rid of the denominator. Multiply through by y squared, so that's -4 times y squared is equal to 45 minus y squared times y squared, y to the 4. And if we move everything to the left hand side, we've got y to the 4 minus 4y squared minus 45 is equal to 0. And now we have the quadratic equation that they were talking about. The question stated by first forming a quadratic equation, we have formed the quadratic equation they asked for. Now we need to solve that quadratic equation. So in this case, I hope you can see that this is just a hidden quadratic, because y to the 4 is y squared squared minus 4y squared minus 45 equals 0. And can we factorize this by side? Looks like we can. So if I put y squared in this bracket and y squared in the other bracket, I'm looking for factors of -45 that add up to -4. So we can do -9 plus 5. Because -9 plus 5, that's -4. -9 times 5, that's -45. And so this means that either y squared is -5 or y squared is 9. This first equation here is a problem because in terms of real numbers, we can't square a real number and then get a negative number, right? So this can't have any real solutions. Or if you prefer to look at it from the other perspective, which is to say that if I take the square root here, I get y is equal to root of -5, and I can't take the square root of a negative number. So this equation has no real solutions. Remember, the question explicitly stated that x and y are real numbers. So y in this case would not be real. So no real solutions there. And so that leaves us with y squared is equal to 9. If we take the square root there, we get y is plus or minus the square root of 9, which is 3. All right. And now that we know what y is, we can come back to this equation here. And that y is -3, we have that x is 3 root 5 over negative 3. So x here would be negative root 5, and that y is positive 3. We have x being 3 root 5 over 3. So x is positive root 5. And so the two square roots are this combination here, which is x is negative root 5 and y is negative 3. So negative root 5, negative 3i, because remember, it's in the form x plus iy. Or we could have this combination here, which is root 5 plus 3i. Root 5 plus 3i. Those are the two square roots of our complex number. Number 6. The variables x and theta satisfy the differential equation dx d theta is equal to 1 over 5x plus 1 times sine squared 2 theta, and x equals 5 when theta is 0. Solve the differential equation and obtain an expression for x in terms of theta. 7 marks. Okay. So we're given this differential equation dx d theta is equal to 1 over 5x plus 1 sine squared 2 theta. The first step when you've got a differential equation is to separate your variables. So we want to put everything that is x on one side, everything that is theta on the other side. So in this case, make sure you're not breaking any algebraic rules when you're doing this, right? So in this case, I want to move this to the left. It's currently multiplying on the right, so it has to divide when it goes to the left. So we now end up with 1 over 5x plus 1. And I want to keep the dx. The d theta, I'm going to move it this side. So on the right-hand side, I end up with sine squared 2 theta, d theta. Okay. And I don't like the way this looks. So I want us to just rewrite that. Let's play around with it a bit. Let's put our denominator over a common denominator, right? So I can write this as 1 over, put everything in the denominator over 5. So I've got x there, and 1 into 5, that goes in 5 times, so x plus 5. And if you resolve this, this just moves to the top. You've got 5 over x plus 5. I think that looks much cleaner. So we can rewrite the left-hand side as being 5 over x plus 5 dx. And this is equal to our sine squared 2 theta d theta. Once you have separated your variables, you integrate both sides. So if we integrate the left-hand side, it becomes 5, the natural logarithm of x plus 5. In this case, if you differentiate x plus 5, you get 1. So you don't have to divide by anything. I mean, technically, you could divide by 1, but you still get the same thing. Plus our constant of integration. And then we need to figure out how to integrate sine squared to theta. The way we're going to do that is we want to use double angle formulas. So we know that if we go to the MF19, cos 2 theta is identical to 1 minus 2 sine squared, not 2 theta, just a single theta. But obviously, this is not exactly what we need. I need to have a sine squared 2 theta. So I can actually manipulate this because this is just a double angle formula, which means that the angle on the left has to be 2 times the angle on the right. So if I want to have 1 minus 2 sine squared 2 theta, then it means that the angle on the left should just be 2 times 2 theta. So I should have cos 4 theta here. And what this allows me to do is to use this equation to rewrite sine squared 2 theta in terms of cos 4 theta. because that's a lot less difficult to integrate. So we can do that. We can make sine squared 2 theta subject of the formula. So we've got 2 sine squared 2 theta is equal to 1 minus cos 4 theta. Divide through by half. You have that sine squared 2 theta is equal to half of 1 minus cos 4 theta. And so what you have is that instead of integrating this, I can just integrate half of 1 minus cos 4 theta with respect to theta. And in fact, we can take the half outside of the integral sign. And now we can integrate. So I've got 5 ln x plus 5. And the reason I've got modulus sign there, I don't think Cambridge will be too fussy about it. But remember that your logarithmic functions can only take positive values. So if x plus 5 ends up being negative, then that's going to be problematic. So that's why I've put in a modulus function there, or an absolute value function, to always make sure that the input we're putting into our natural logarithm is always positive. But if that doesn't make sense, don't worry too much about it. So we've got half. Integrate 1, you get theta. Integrate cos 4 theta, you get, integrate negative cos, you get negative sine. And this is 4 theta. Differentiate the inner function, which is the 4 theta, you get 4, so divide by that 4. Okay. And so we have that 5 natural log of x plus 5 plus c is equal to half theta minus 1 over 2 times 1 over 4. So 1 over 8 sine 4 theta. But of course, we need to evaluate our constant of integration. And so that's why they gave us this extra information. X is 5 when theta is 0. X is 5 when theta is 0. So we have 5 ln 5 plus 5 plus c is equal to, when theta is 0, so this whole thing falls away, because sine 0 again is 0, theta, or 0 times half is 0. So you've got 5 ln 10 plus c is equal to 0, so c is equal to negative 5 ln 10. And so that means our solution to the DE is 5 ln x plus 5 minus 5 ln 10 is equal to half theta minus 1 over 8 sine 4 theta. But if you read the question again, you notice that they said solve the DE and obtain an expression for x in terms of theta, which means that we have to make x the subject of the formula. So to do that, let's start by moving this to the right hand side. So 5 ln mod x plus 5 is equal to, that's going to be half theta minus 1 over 8 sine 4 theta, and that's going to be plus 5 ln 10. And then divide both sides by 5, so you've got ln x plus 5 is equal to 1 over 2 divided by 5 becomes 1 over 10 theta minus 1 over 8 divided by 5 becomes 1 over 40 sine 4 theta. And then 5 ln 10 divided by 5 is just ln 10. And now we can apply the exponential function to both sides. So we've got e of this whole thing, and we've got e of this whole thing. So if we take e, that cancels with the ln, and you just end up with your x plus 5. And this is equal to, here we've got e to the 1 over 10 theta minus 1 over 40 sine 4 theta plus ln 10. What we want to do here is I want you to keep in mind that if you've got e to the power of a plus b, this is the same as e to the a times e to the b, laws of indices, right? So I want to apply that with this being my a and this being my b. So I have that x plus 5 is equal to e to the 1 over 10 theta minus 1 over 40 sine 4 theta times e to the ln 10. And the reason I've done that is because I know that e and ln will cancel out. So what you end up with is x plus 5 is equal to this part just becomes 10 and it's multiplying that part. So 10, I'm actually going to use, instead of using the e to the x notation, I'll use this notation. I think it would be easier to read. So 10 times the exponential of 1 over 10 theta minus 1 over 40 sine 4 theta, and subtract 5 from both sides. So x is equal to 10 the exponential of 1 over 10 theta minus 1 over 40 sine 4 theta, and that is minus 5. And that there is the solution to our DE. Number 7. The diagram shows the curve y is equal to x cubed cos 2x, for x is between 0 and a quarter pi. The curve has a maximum point at m, so already when I hear maximum point, I'm already thinking at m, my dy dx has to be 0. That's going to be useful somewhere, somehow. Okay. The curve is a maximum point at m where x is equal to p. Part A says, show that p satisfies the equation p is equal to half arctan of 3 over 2p. Okay. So questions like these are pretty much asking you to get creative and find a way to see how from the information they've given you, you can come up with this equation. So like I mentioned, because I've heard that m is a maximum point, that's a stationary point, dy dx is 0. So I'm already thinking that if I differentiate my curve, I get dy dx and I equate it to 0, then I've got somewhere to start, right? And p is clearly the x coordinate at our stationary point. So once I get dy dx, I can probably change my x to p if I'm interested in the stationary point. So let's start there. Let's just start by finding our dy dx. So we have that y is x cubed cos 2x. And because we're following this idea, we need to find dy dx. So this is a product. So hold the x cubed first, then differentiate the other function. So if you differentiate cos 2x, you're going to get that differentiate cos, you get negative sine. So negative sine 2x. And then because this also has a function inside of it, you have to differentiate the inner function. So differentiate 2x, you get a 2, so multiply by 2. Okay. And then now we're going to hold the cos 2x. And we want to differentiate the x cubed. If you differentiate x cubed, that's going to be 3x squared. And so now what you have is that dy dx is equal to negative 2x cubed sine 2x plus 3x squared cos 2x. And now, if we follow the trail, we know that at m dy dx is 0. At m, our dy dx is 0. So at the point M, we have that negative 2x cubed sine 2x plus 3x squared cos 2x. This is all equal to 0, right? And then what we also know is that at this point M, our x coordinate is actually P. So I can even go ahead and substitute x with P because we know that x is P at this point. So that becomes negative 2p cubed sine 2p plus 3p squared cos 2p is equal to 0. And now it really is just a question of how creative are you to get to the actual equation that they want you to get. So the way I would think about this is that I can tell that I've got sine and cos, and clearly I need to find a way to end up with tan. The only link I know between those two is that tan x is identical to sine x over cos x. So somehow I'm going to need to force a sine x over cos x to end up with tan. And we can actually do that. And for starters, I'm just going to move this to the right hand side so that it's positive. So I end up with 2p cubed sine 2p is equal to 3p squared cos 2p. And so like we mentioned, we want to force a sine x over cos x situation. So I can literally just divide both sides by cos 2p. Because now that gives me what I want on the left hand side, which is sine 2p over cos 2p, that's tan 2p. And on the right hand side, the cos 2p's just cancel out. So what I end up with is 2p cubed tan 2p, and this is equal to 3p squared. And here, so in the brackets, you notice that we've got 3 over 2p. So it makes sense. I can see this 3 and I can see this 2 here. It makes sense for me to divide both sides by 2p cubed. So I can say tan 2p is equal to 3p squared over 2p cubed. So that I've got this 3 over 2 ratio that I'm seeing there. And the p squareds actually cancel out nicely. So p squared will cancel out the cubed and you're only left with 1p down there. So now we have that tan 2p is equal to 3 over 2p. And at this point, you've pretty much gotten what you wanted. So just apply arctan on both sides. You have that 2p is arctan of 3 over 2p. And multiply both sides by half. You have that p is equal to half of arctan of 3 over 2p. And that is exactly what the question wants from you. Part B then goes on to say, show by calculation that p is between 0.5 and 0.7. So to do a question like this, all you need to do is to take the equation that you had in part A and put everything on one side and make a function out of it. So I'm going to say let f of p be the function. I'll move the p to the right hand side so that I've got half arctan of 3 over 2p minus the p. And now if we want to check if a root or if our root p lies between 0.5 and 0.7, what we can do is to just evaluate this function at 0.5 and at 0.7. And if we get a sign change, then a root lies between there. And the basic idea is that if you look at a graph, right, and you've got something like this, let's say this here would be your 0.5, and then this here would be 0.7. So you can tell that the value of the function at 0.5 is clearly positive, but the value of the function at 0.7 is negative. So if there's a difference in the sign on your function, it means that it has to have crossed the x-axis at some point. And whenever we cross the x-axis, there is a solution. So when we're checking for a sign change, what we're actually checking is, has our function crossed the x-axis? Because if it crossed the x-axis, then at some point our function was equal to 0. And when our function is equal to 0, we have a solution. So that's what we want to do. So we're going to do f of 0.5 is equal to 1 over 2 arctan of 3 over 2 times 0.5 minus 0.5. Punch this into the calculator. That's 1 over 2 arctan of, make sure you are in radians, 3 over 2 times 0.5 minus 0.5. And this gives me 0.1245, more importantly, plus. And then f of 0.7 is equal to half arctan of 3 over 2 times 0.7 minus 0.7 is equal to, so half of arctan 3 over 2 times 0.7 minus 0.7 is equal to negative 0.1329 and so on. So clearly we do have a sign change, which means that our function has crossed the x-axis and there must be a solution between 0.5 and 0.7. So we can conclude that, therefore, since there is a change in sign, the root in this case p lies between 0.5 and 0.7. Now, part C says use an iterative formula based on the equation in part A to calculate p correct to 3 decimal places. Give the result of each iteration to 5 decimal places. Okay. So the equation we had in part A was that p is equal to half arctan of 3 over 2p, and we're using this as our iterative formula. So we can just rewrite this as Pn plus 1 is equal to half arctan of 3 over 2Pn. Okay, so we need to pick an initial value to start our iteration. In this case, we know that our P lies between 0.5 and 0.7. So as my starting value, I can use either 0.5 or 0.7. In this case, I'm leaning towards using the midpoint of 0.5 as 0.7, because the closer this value is to 0, then the closer we are to the actual solution. Because if you look at our diagram here, the closer I get to 0, to a function value of 0, the closer I am to my actual function. So that's why I'm tempted to use the midpoint. But to be honest, you can use 0.5 and 0.7. It just might take a little longer for your sequence to converge. So in this case, I'm going to use 0.6. But again, 0.5 and 0.7 would work just as well. Okay, if you pick a value that's too far out, your sequence may never converge, or it may converge to some other solution. So just be careful with that. Just make sure that it's close enough. So if P0 is 0.6, P1 is going to be half of arctan 3 over 2 times P0, which is 0.6. And this gives us 1 over 2 arctan of 3 over 2 times 0.6 and they say they want the result of each iteration to 5 decimal places. So 0.59514. And if we go for our next iteration, we're going to do half arctan of 3 over 2 times the result of your previous iteration. So we can use this cool button on our calculator, which is the ANS button. So where you previously had 0.6 or 0.5 or 0.7, depending on what your P naught was, you're going to replace that with ANS. And ANS just has the result of your previous calculation. In this case, our previous calculation denotes the previous iteration. So now you just simply press equals and you get 0.59654 to 5 decimal places. We want our answer will be to 3 decimal places. Okay, so we're not quite there. Don't change anything on your calculator, simply press equals. You get 0.59614, and we're quite close. It hasn't converged yet. Very close. Press equals again. 0.59626. It looks like it's converged because this here to 3 decimal places is 0.596. This here to 3 decimal places is again 0.596. This was 0.597. That's why we didn't take it. So we can conclude that therefore P is equal to 0.596, correct to 3 decimal places. Number 8, we're given that two lines have equations. R is equal to, that's -1, 3, -4, plus lambda 2, 3, -1, and R is equal to 2, -3, -1, plus mu, -1, -2, 1. Part A says, show that the lines are skew. Okay, so if lines are skew, it means that they are not parallel and they do not intersect. So the first thing that we have to show is that they are not parallel. Lines are parallel if their direction vectors are scalar multiples of each other. In other words, if I take these two direction vectors, I can tell that there is no number that I can multiply -1, -2, 1 by to get 2, 3, 1, right? Like it's just not possible. If I do 2 here, I'm going to get -2, -4, and 2, which clearly is not the same as 2, 3, 1. So there's no way for me to find a scalar to multiply this by to get 2, 3, 1. And so for that reason, these are not scalar multiples. A good way to argue this out is to just use ratios and say that if I take -1 divided by 2, this is clearly not equal to -2 divided by 3. This is also not equal to 1 over 1. Hence, not parallel. You can use either this argument, should have put a not equal to sign there, or you can use the ratios argument. The ratios it's a stronger argument because if these are scalar multiples, for example, if you've got 1, 2, 3 and 2, 4, 6, right? These are clearly scalar multiples. I should have written 2 times. 2 times 1, 2, 3 is equal to 2, 4, 6. So clearly scalar multiples. So if you had two lines where one of them had this direction vector and the other one had this direction vector, they would be parallel. And if you check the ratios, here you would say 1 over 2, and you check 2 over 4, 3 over 6. The ratios are clearly equal, so it must mean they are parallel. Okay, because 2 over 4 is half, 3 over 6 is half. Right. So our ratios are not equal, so our lines are not parallel. now we need to prove that they do not intersect. So if we take our two lines, and I want to first write them in component form, which means I'm just going to write them as one big vector. And I can do that by saying -1 plus lambda times 2, that's the x component. 3 plus lambda times 3, that's the y component. -4 plus lambda times -1, that's your z component. And we'll do the same for the other line. We've got 2 plus mu times -1, that's 2 minus mu. -3 plus mu times -2, that's -3 minus 2 mu. -1 plus mu times 1, that's -1 plus mu. And now what we can do is write this as what we call parametric equations, which is just a fancy word for saying this component there represents the x component. So x is -1 plus 2 lambda. And then this is y, this is z. So y is equal to 3 plus 3 lambda. And then z is equal to -4 negative lambda. And we can do the same. Here x is 2 minus mu, that's your x component. Y is -3 2 mu. And z is -1 plus mu. To be fair, you can just jump straight to the parametric equations from this vector equation form if you're comfortable with doing that. But if you're not, first write it in component form and then get your parametric form. But now, once we're here, I hope you can see that we can create a system of equations. I can say that my x component is equal to this, but we also know that x is equal to that. So I can equate those two. Right? X is equal to, y is equal to 3 plus 3 lambda, but y is also -3 2 mu. Z is -4 minus lambda, and this is equal to -1 plus mu. And so if these two lines intersect, then all three of these equations must hold. So we can use two of the equations to find lambda and mu. And if we substitute lambda and mu into the third equation, and both sides of the equations are equal, then they intersect. However, if the sides are not equal, then they do not intersect. So just label this equation 1, equation 2, equation 3. I'm going to use, just so that it flows nicely, let's use equation 1. And what we want to do with equation 1 is we want to make mu subject of the formula. Right? So I'm going to say mu is equal to, move the negative mu that side and everything moves to the right. It becomes +1 minus 2 lambda. So mu is equal to 3 minus 2 lambda. And now I can substitute that into equation 2 and evaluate what lambda is. So using equation 2, I can say 3 plus 3 lambda is equal to -3 minus 2 mu. From equation 1, we know that mu is 3 minus 2 lambda. And so we can simplify. This is 3 plus 3 lambda is equal to -3. -2 times 3, -6. -2 times -2 lambda, that's 4 lambda. So we've got 3 plus 3 lambda is equal to, that's -9 plus 4 lambda. And if we make lambda subject of the formula, move that there, move that there, got lambda is equal to 3 plus 9, which is 12. Okay. And if we go back to equation 1, mu is 3 minus 2 lambda, so mu is 3 minus 2 times 12, and so mu has to be That's 3 minus 24, so minus 21. So if these lines truly intersect, I should be able to substitute mu equals negative 21 and lambda equals 12 into this third equation, and the left-hand side should be equal to the right-hand side. If you do it with these first two equations, obviously it's going to be correct because I used these first two equations to calculate mu and lambda. But the true test is to substitute in the one equation that you haven't actually used to see if that actually holds true. So using our third equation, we have negative 4 negative lambda is equal to negative 1 plus mu. So if I substitute, negative 4 negative lambda being 12 should be equal to negative 1 plus mu being negative 21. And so if we simplify this, negative 4 negative 12 is negative 16. Is this equal to negative 22? No, it is not equal. So we can say that not all three equations are satisfied. Not all three equations are satisfied. Are satisfied. So the lines do not intersect. And earlier we proved that the lines are also not parallel. So since lines are not parallel and do not intersect, they are skew. And that would be our final answer. Part B. So B says find the obtuse angle between the directions of the two lines. Okay. So the first direction vector, which I'll call D1, is, well, direction vectors. It's the 2, 3, negative 1. So our first direction vector is 2, 3, negative 1. And then our second direction vector, which I'll call D2, is, where is D2? Is negative 1, negative 2, 1. Negative 2, already forgotten it. Negative 1, negative 2, positive 1. Okay. Negative 1, negative 2, positive 1. Okay, perfect. If you're not familiar with this notation, this just means that this is a vector. Do not worry about that at all. Okay, so we want to find the obtuse angle between the directions of the two lines. So obtuse means that is between 90 and 180 degrees. And to find angle between two vectors, we use cos theta is equal to the dot product of the two vectors, in this case, the dot product of D1 and D2 over the moduli of D1, D2 multiplied. Right? This should be an equal sign. So let's first find their dot product. So D1 dot D2 is equal to, that is 2, 3, negative 1 dot negative 1, negative 2, 1. This is equal to 2 times minus 1, that's minus 2, plus 3 times minus 2, that's minus 6, plus minus 1 times minus 1, that's minus 1. So that's negative 2, negative 6, negative 1, which is negative 9. That's our dot product. Now we need to find the magnitude of D1, which is just the square root of 2 squared plus 3 squared plus negative 1 squared, right? And so that gives us, that's 4 plus 9, which is 13 plus 14, so root 14. And then for D2, this is going to be the square root of 1 squared plus 2 squared plus 1 squared. 1 squared plus 2 squared plus 1 squared. So that's 1 plus 4, which is 5 plus 1 root 6. So going back to our formula, we have that cos theta is equal to the dot product, which is negative 9, over the product of the moduli, so root 14 times root 6. And so we can say theta is arc cos of negative 9 over root 14 times root 6. Here they have not specified whether we should be in degrees or radians, so you can go either way. I am in degrees because I want to make sure that I can see my angle is obtuse. So that's arc cos of negative 9 over root 14 multiplied by root 6, which gives us theta is 169.1 degrees. Or if you did it in radians, then you should be getting 2.95 radians. Oh, both answers work since they haven't specified. Number 9. The polynomial 6x cubed plus ax squared plus bx plus 9 is denoted by p of x. So we're given that p of x is 6x cubed plus ax squared plus bx plus 9, where a and b are constants. Okay. It is given that x minus 3 is a vector. X minus 3 is a vector of p of x. And when the first derivative, p prime of x, is divided by x minus 3, remainder is 72. Okay, so when the first derivative is divided by x minus 3, remainder is 72, then part A says find the values of a and b. So here we have to use the factor and remainder theorem. So the factor theorem, or rather let me start with the remainder theorem. The remainder theorem states that if a polynomial p of x, if a polynomial p of x is divided by x minus a, then p of a is equal to the remainder. Or in other words, the remainder is equal to p of a. Right? That is the remainder theorem. Then the factor theorem states that if p of x is divided by a factor x minus a, then p of a is equal to 0. And I hope you can see that the factor theorem follows on from the remainder theorem, because if you divide something by a factor, there is no remainder. So the remainder is 0, right? So this is just a special case of the remainder theorem. So let's see if we can apply this to our case. So the first part here, we have our p of x, and we're told that x minus 3 is a factor of p of x. So according to the factor theorem, this means that p of a, in our case a is this 3 here, has to be equal to 0 by the factor theorem. And then the second part that we have is that p prime of x is divided by x minus 3 and the remainder is 72. So we need to actually first find what p prime of x is. So p prime of x, if we differentiate, because remember prime means first derivative, if it's double prime it's second derivative. So p prime of x is equal to, differentiate 6x cubed, you're going to get 6 times 3, which is 6, 12, 18, x squared, plus, bring down the 2, so 2ax. If you differentiate bx, you just end up with b. If you differentiate the constant 9, you get 0. So we are told that when p prime of x is divided by x minus 3, the remainder is 72. So here we have to use the remainder theorem. So in our case, our polynomial here is p prime of x, and our remainder here is 72, and our a here is the 3. I hope that makes sense. So it means we also get that this should be p prime, by the way, in this context. So this would be that p prime of 3 has to be equal to 72 by the remainder theorem. And so now, if we just substitute in the polynomial, p of 3 is equal to 0, so substitute x with 3 here. So that's 6 times 3 cubed plus a times 3 squared plus b times 3 plus 9, and this is all equal to 0. So 3 cubed, that's 3, 9, 27 multiplied by 6. That gives us 162 plus 3 squared, that's 9 times a plus 3b plus 9 is 0. Okay. And so we've got 162 plus 9, which is 171. So I have 9a plus 3b. And then I'll move this to the right-hand side. So that's equal to negative 171. So we've got one equation in terms of a and b. And of course, the second equation will come from p prime of 3 is equal to 72. So if we go back, let's bring this p prime down a bit. So if we substitute 3 into p prime, we've got 18 times 3 squared plus 2a times 3 plus b, and this is all equal to 72. So if we do 18 times 3 squared, we've got 162 plus 2a times 3, so 6a plus b is equal to 72. So we've got 6a plus b, move the 162 to the other side. 72 minus 162 is minus 90. And now we've got these two nice equations in terms of a and b that we can solve simultaneously. So we can make b subject of the formula here and say b is negative 6a, negative 90. Then we can substitute it here. So now it's 9a plus 3 times negative 6a, negative 90 is equal to negative 171. And so 9a, you've got 3 times negative 6a, which is negative 18a. Got 3 times negative 90, which is negative 270a. Or there's no a, just negative 270. And this is equal to negative 171. 9a minus 18a, that gives us negative 9a. And minus 270 equals minus 171. I'll move this there and this side. So I've got 9a is equal to 171 minus 270, which gives us negative 99. Divide both sides by 9. We give that a has to be negative 11. So if we substitute a back in, we have that b is equal to negative 6 times negative 11 minus 90. So that becomes 66 minus 90. So b is minus 24. And so we have that A is negative 11 and B is minus 24. And that's that for part A. Part B says when A and B have the values found in part A, factorize P of X completely. Okay. So that means P of X becomes 6x cubed minus 11x squared minus 24x plus 9. So P of X becomes 6x cubed minus 11x squared minus 24x, and what else was there? Plus 9, right? And what they want us to do is to factorize P of X completely. So from part A, we know that, or rather from the stem of the question, we know that x minus 3 is a factor of P of X, right? X minus 3 is a factor. So what I can do is I can divide P of X by x minus 3 to find what the other factor is. And because my polynomial is to the power 3, I have a linear factor, so the other factor has to be a quadratic factor, because remember your powers must add up to 3. 1 plus 2 is 3. So I can do polynomial division to find my quadratic factor. And once I have that quadratic factor, I can then factorize the quadratic, and that allows me to factorize completely. So let's start by doing the polynomial division. So I've got x minus 3, and this is dividing 6x cubed minus 11x squared minus 24x plus 9. By the way, you can do this by inspection if you're comfortable with inspection. Otherwise, do polynomial division. So remember, for polynomial division, in our divisor, we pick the term that is the highest degree, and that's what we're going to divide by. So we're going to say how many times does x go into 6x cubed? That's 6x squared minus, now multiply the 6x squared by your divisor. So 6x squared times x, that's 6x cubed. 6x squared times negative 3, that's negative 18x squared. Subtract 6x cubed minus 6x cubed, 0, minus 11x squared minus 18x squared. So that's minus 11 plus 18, 18 minus 11, which is 7x squared. Bring down the negative 24x plus 9. How many times does x go into 7x squared? That's 7x minus, that's going to be 7x times x, which is 7x squared. 7x times negative 3, that's minus 21x. And 7x squared minus 7x squared is 0. Minus 24x plus 21x is minus 3x. Bring down the 9. And how many times does x go into negative 3x? We get negative 3. So negative 3 times x, that's negative 3x. Negative 3 times negative 3, that's positive 9. And hopefully you can see that these two cancel out and give you 0. And you expect that to happen because you are dividing by a factor, so the remainder has to be 0. And whatever you have at the bottom here is the remainder. So if you do this and you end up with a number for your remainder or some expression as your remainder, just check your work again. Chances are you've made a mistake. Okay, so the quotient here, that becomes the other factor. So x minus 3 is a factor of P of x, and 6x squared plus 7x minus 3 is a factor of P of x. So what that means is that I can write P of x as a product of its factors. I can write P of x as x minus 3 multiplied by 6x squared plus 7x minus 3 is equal to P of x. So if you think about it, really, it's the same as saying if you've got 6, you can write it as a product of its vectors. That's simply what we've done here. And what this allows us to do is our question wants us to factorize p of x completely. So we are halfway there. We still need to factorize this quadratic here. Because once we factorize the quadratic, then we have completely factorized p of x. So let's take our 6x squared plus 7x minus 3, and we need to factorize it. So let's see what's the approach here. So we could do 2x and 3x, and I want factors of, I could put a 3 here, 3 and 1. And what we want to do is we want to say positive 9x minus 2x gives me 7x. The idea I've used here, if you can't factorize it by side like this, I'll give you a few options of how you can get away with, 1, running away from factorization, or 2, how you can actually factorize it step by step. But what I've done here is to say, I'm going to put 2x and 3x here because 2x times 3x gives me 6x squared. Then if I take 2x and I multiply it by negative 1, let's maybe use a dot here so that it's not confusing. If I take 2x and multiply it by negative 1, then I take 3 and I multiply it by 3x. I know that this has to add up to 7x because this is negative 2x plus 9x, which gives me the 7x, right? And the 3 and negative 1, I've chosen them because they are factors of negative 3. But if you're not too experienced with factorization, that may be a bit difficult to just try to reason it out like that. So there's 2 options that you can do as an alternative to this. If you never want to factorize and you die by the quadratic formula, then this is the approach that you can take. You can use the quadratic formula as normal and say x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a, so 2 times 6. So you get x is equal to, that's negative 7 negative root 7 squared minus 4 by 6 by negative 3 over 2 times 6, which is negative 3 over 2. That's one of your solutions. And the other one will be 1 over 3. And what you're going to do is to work backwards. First, get rid of the denominator because we don't want a fraction. So multiply, if we look at this one, multiply both sides by 2 so that you have 2x is negative 3. And then move the negative 3 to the other side. So you've got 2x plus 3 is equal to 0. For this one, do the same thing, get rid of the denominator, multiply both sides by 3, you get 3x is 1, and then you end up with 3x minus 1 is equal to 0, and then just put the 2 together, 2x plus 3 multiplied by 3x minus 1, that's your factorization as above. So this is for those who never want to factorize in their life. I wouldn't advise doing this, but if you're caught in a tricky situation, you don't know how to factorize, and you desperately need to factorize, you can still just use the quadratic formula and then reverse it to get what the factorization would look like. But if we are going to actually factorize, what we can do, you've got 6x squared plus 7x minus 3. We can use The AC method, it's got many names. I forgot the other names, but I learned it as the AC method, which is to say multiply 6 and negative 3, right? When you've got a quadratic, you've got ax squared plus bx plus c. So you want to get AC. Multiply 6 by negative 3, you get negative 18. So I need factors of negative 18 that add up to my 7x here. So negative 18, I'm thinking 6 and 3, not quite. 9 and 2 could work. So I need to structure them so that they add up to negative 7. So I know that I have 9 and 2, right? So, or specifically, I have 9 times negative 2. That gives me negative 18. But if I take it as 9 minus 2, that is 7. So I know that I can write 7x as 9 minus 2x, right? So we just go back to our quadratic and we've got 6x squared plus replace the 7x with this new expression here. So that becomes 9x minus 2x minus 3. And now we're going to factorize by grouping, which means factorize these two by themselves and then factorize these two by themselves. So if I factorize the first lot, I can factor out a 3x, and then I've got in the brackets here, that becomes 2x, and that there becomes a positive 3. And then for the second one, your inner bracket has to match the first bracket that you have. So it has to be 2x plus 3 here. And so what do I have to factor out here? For me to get a 2x plus 3, I have to factor out the negative. And so now, since 2x plus 3 is common in both terms, I can actually just factor out the 2x plus 3. And so here I end up with 3x minus 1, which is the same result as the other two scenarios. So pick your poison. Either learn how to properly factorize, and then once you've done it, you can pretty much skip most of the steps once you're comfortable with factorization and do it mentally. Or you can just stick to the quadratic formula and never factorize a day in your life. And so we actually haven't finished the question. So the complete factorization of p of x becomes the x minus 3 that we have here times the factorization for the quadratic, which is 2x plus 3 times 3x minus 1. And that there is the complete factorization of p of x. So part C, now we're told hence solve the inequality p of x is less than 0. So in part B, we already deduced that p of x can be written as this. So we can write this as x minus 3 times 2x plus 3 times 3x minus 1 is less than 0. And the way we're going to solve this is by using a sign line, right? So the first step is we're going to figure out what are all our critical points, or in other words, when can this whole thing be equal to 0? It can be equal to 0 when the first bracket is 0, so when x minus 3 is 0, or when the middle bracket is 0, or the third bracket is 0. So if the first bracket is 0, then we get x is 3. If the second bracket is 0, we get 2x is equal to negative 3, so x is equal to negative 2/3, negative 3 over 2. And in the third case, x is a third, right? And what you're going to do is you're going to draw a line, a number line, and you're going to mark each of these points on your number line. So I'll start with the smallest being negative 3 over 2. And then we've got next we'd have 1 over 3. And lastly, we'd have a 3. And so what I'm going to do is I'm going to write each of these brackets, the x minus 3, 2x plus 3, and 3x minus 1. And what you do now is you're going to look at each bracket. So x minus 3, when is that positive and when is that negative? So when x is less than negative 3 over 2, this is always going to be negative, right? Because if I take x is, let's say x is negative 2, I end up with negative 5, which is negative. And when x is between negative 3 over 2 and a third, this is still negative. When x is between a third and 3, x minus 3 is still negative. It only becomes positive when x is greater than 3, right? So this is now positive. And we'll do the same for all the three scenarios. So 2x plus 3, when x is less than negative 3 over 2, then this is going to be a good way to approach this actually is to just figure out when is this positive. 2x plus 3 is greater than 0. If you do 2x is greater than negative 3, x is greater than negative 3 over 2. So as long as x is greater than negative 3 over 2, this is always going to be positive. Otherwise, it's negative, right? And you could have done the same for x minus 3. X minus 3 is greater than 0. So x greater than 3. So this is only positive, i.e. bigger than 0, when x is bigger than 3, which is why we only had a positive there. And we can do the same for 3x minus 1. When is this positive? When x is 3x greater than 1, so when x is greater than a third. So when x is greater than a third, so positive here, and negative otherwise. And our question here, in our expression, we're saying when is p of x less than 0? So remember, these things are multiplying. So for me to get something that's less than 0, it means that this whole thing, when multiplied together, should result in a negative number. So if my first bracket is negative, and the second bracket is negative, and the third bracket is negative, I'm multiplying a negative by a negative, right? By a negative. So the first two negatives will cancel out. And so you end up, overall, what we end up with is going to be a negative solution. So I know that this here, this combination would give me a negative answer, would give me something less than 0. If I look at the next situation here, I've got a negative and a negative being multiplied together. That becomes positive, and it's multiplying a positive. So this just ends up being positive overall, i.e. greater than 0. However, if we come to this next region here, I've got a negative multiplied by a positive by a positive. So overall, this is negative. Right, so maybe let's write that down. This is negative. This is positive. This there is negative. And the last scenario here, they're all positive. So the two scenarios that we want are these ones. And those are the regions when x is less than negative 3 over 2, as well as the region when x is in here, right? When x is between a third and 3. Those are the two regions such that when I multiply these three brackets together, I get a negative result. Number 10, let f of x equal negative 7x squared plus 2x minus 6, and this is all over 1 plus x multiplied by 4 plus x squared. And part A says express f of x in partial fractions. Okay, so we've got negative 7x squared plus 2x minus 6. We have to inspect our factors. So this is a linear factor. So that means this becomes a over 1 plus x plus This is a quadratic vector. So this becomes bx plus c over quadratic, 4 plus x squared. And now we're going to multiply through by 1 plus x times 4 plus x squared to get rid of all the denominators. So on the left, you just end up with negative 7x squared plus 2x minus 6. And on the right, it becomes a multiplied by the 4 plus x squared plus bx plus c multiplied by 1 plus x. And now we're going to try to eliminate one of the terms so we can evaluate one of the unknowns. So for example, if we make x here negative 1, this would make this bracket 0. And so this whole thing would fall away because this bracket is being multiplied by 0. So that eliminates that term there. And that allows us to evaluate a. So we can say let x equal negative 1. So on the left, we've got negative 7 times negative 1 squared plus 2 times negative 1 minus 6 is equal to a multiplied by 4 plus negative 1 squared. Okay. So the left-hand side simplifies to negative 7, negative 2, negative 6, which is negative 15. And on the right, we've got 4 plus 1, which is 5, so 5a. Divide both sides by 5. You get a is negative 3. So now we know what a is. We can say let x equal 0. And this allows us to eliminate the b term. A, we already know what that is, so we can just substitute a. And that gives us the opportunity to evaluate c. So on the left, this falls away because we're multiplying by 0. This also falls away. So you've got negative 6 is equal to a, which we know is negative 3, times 4 plus 0 squared. So 4 plus the bx part, that falls away because we're multiplying b by 0. So we've just got the c, and this is multiplying 1 plus 0. So it just times 1. And so we've got negative 6 is equal to negative 12 plus c. So c has to be 12 minus 6, which is 6. And now that we have a and c, we can literally just choose any value for x to allow us to evaluate b. So we can say let x equal 1. And so now it becomes negative 7 times 1 squared plus 2 times 1 minus 6 is equal to a. We know that a is minus 3 times 4 plus 1 squared plus b times 1 plus c, which is 6, times 1 plus x, which is 1. And then we simplify. So on the left, we have minus 7 plus 2, which is minus 5, minus 6, which is minus 11. And then that's 4 plus 1, 5 times minus 3, minus 15. And then we've got plus, this here is 2, multiplying the brackets, so 2 times b, that's 2b, 2 times 6, that's a 12. Okay. And we can simplify this further. Negative 11 is equal to negative 15 plus 12, that's negative 3 plus 2b. And so we've got 2b is equal to, if you take the negative 3 to the other side, that's negative 11 plus 3, which is negative 8. Divide both sides by 2. You get that b is negative 4. And so what this means is that f of x can be written as a over 1 plus x. A is negative 3 over 1 plus x plus bx plus c. B is negative 4x plus c. C is 6. And this is all over 4 plus x squared. And these are the partial fractions for f of x. And that's our final answer. Part B says, hence find the exact value of the integral from 0 to 2 of f of x with respect to x. Give your answer in the form a pi minus ln b, where a and b are constants. 6 marks. Okay, so instead of integrating the original f of x function that we were given at the beginning of this question, this one, Cambridge led us on by telling us to first decompose into partial fractions, because it's easier for us to integrate the partial fractions instead of the actual original function. So that's what we are going to do. So we want to integrate from 0 to 2 our function -3 over 1 plus x plus -4x plus 6 over 4 plus x squared, and this is all with respect to x. Okay, maybe for now just ignore the limits so that we get the integral first, and then we'll bring back the limits. So let's start with the integral of -3 over 1 plus x, right? That's just going to be -3, the natural logarithm of your 1 plus x. And if we do, we can split this fraction into 2. So we can distribute the denominator and have this as -4x over 4 plus x squared with respect to x. And then the other part would be 6 over 4 plus x squared with respect to x. Okay. And so for this part specifically, let's do that on the side. We've got the integral of -4x over 4 plus x squared with respect to x. So the idea we want to use here is k f prime of x over f of x with respect to x is equal to k ln f of x. This is what we want to use, right? If you differentiate your denominator and you find that your numerator is the derivative of your denominator, then you can use this form. If we differentiate our denominator here, if you differentiate 4 plus x squared, you get 2x. Notice that that's not exactly what our numerator is, but we can force that. So if I differentiate 4 plus x squared, I get a 2x. But in reality, I've got a -4 on my numerator. So to maintain that -4, I can just multiply by a constant outside, because -2 times 2x is still -4x. But now what this allows me to do is to write it in this form, to say that if I differentiate my denominator, I get the first derivative on my numerator, which is the case here. If you differentiate 4 plus x squared, you get 2x. And then it's being multiplied by some constant k outside the integral sign. And so what this means is that if I differentiate this, I get k, which is -2, the natural logarithm of f of x being your denominator. So 4 plus x squared. Okay, so that's that part. And then we also need to deal with this part here, which is the integral of 6 over 4 plus x squared with respect to x. And here what you're going to use is the integral of 1 over x squared, or rather let me write it as over a squared plus x squared with respect to x. This is in the MF19. 1 over a arctan of x over a. So we need an a squared plus x squared in our denominator, which we have because 4 is just the same as 2 squared, right? So that means if I integrate this, what I'd get is 1 over a, my a is 2, and remember it's multiplied by this 6, because the 6 you can just take the 6 outside as a constant and then put a 1 there. So the 6 is multiplying everything, times 1 over 2 arctan of x over a is 2. And that is our integral. 6 times half, that's 3. So now, putting everything together, we've got the negative 3 ln 1 plus x, and then we've got the red result, negative 2 ln 4 plus x squared, negative 2 ln 4 plus x squared, and then we've got the green result plus 3 arctan of x over 2. Now we can bring back our limits. This is from 0 to 2. All right, so let's substitute in our limits. We start with the upper limit. So that's negative 3 ln 1 plus 2 minus 2 ln 4 plus 2 squared plus 3 arctan of 2 over 2 minus, we'll do the lower limit. So that's negative 3 ln 1 plus 0 minus 2 ln 4 plus 0 plus 3 arctan of 0. Okay, so let's simplify this step by step. So negative 3 ln 1 plus 2, that's negative 3 ln 3. Then we've got negative 2 ln 4 plus 2 squared, which is 4. So negative 2 ln 8. 3 arctan of 1, 2 over 2 is 1. So arctan of 1 is a quarter pi, and that's being multiplied by 3. So 3 over 4 pi minus the lower limit. So here we've got negative 3 ln 1. Ln 1 is 0. Then we've got negative 2 ln 4. 3 arctan of 0. Arctan of 0 is 0. All right. So we've got negative 3 ln 3, negative 2 ln 8, and then we've got positive 2 ln 4, and plus the 3 over 4 pi. Then what I'm going to do is I'll start by combining these two first, since they have the same coefficient, the 2. So if we take those aside, I've got 2 ln 4 minus 2 ln 8. So because they have the same coefficient, I can just combine them using my laws of logarithms. So this here is going to use ln a minus ln b is ln a over b. So that becomes 2 ln 4 over 8, or 2 ln 1 over 2. And so now what we have is we've got negative 3 ln 3, and then this we have combined to positive 2 ln half plus 3 over 4 pi. And keep in mind that our final answer has to be of the form a pi minus ln b. So the a pi part, we already have that. We just need to figure out this negative ln b part. So I know that I have to maintain a negative sign on my logarithms. So what I'm going to do is first, I'm just going to get rid of these coefficients here by using the law of logarithms that says ln a to the n is equal to n ln a, except we want to use it in the other direction. Right, so this 3 can go up and it becomes negative ln 3 cubed. This 2 can go up, so that is plus ln half squared, right, plus the 3 over 4 pi. Negative ln 3 cubed is 27, and then we've got plus, that is ln a quarter, that's 3/4 pi. And now let's just focus on our logarithms here. I want to preserve a negative sign, so I'm just going to factor out the negative sign, right? So that what I have here is ln 27 minus ln a quarter plus the 3 over 4 pi. And then inside the brackets, I can just use the law of logarithms we just used just now. Ln a minus ln b is ln a over b. And so that becomes negative in the brackets ln 27 divided by a quarter. And then close the brackets plus 3/4 pi. So this is negative ln 27 divided by a quarter. That's 27 by 4, which is 108 plus 3/4 pi. And so therefore our final answer is 3/4 pi minus ln 108.
By the way, if you like the way that I break down questions, there's also a good chance you like the way that I tutor. I run a one-on-one tutoring program where I help E and D students transform their grades into A's and A stars so that they can get in their dream university. So if you want that to be you, click the first link in the description down below and I'll make it happen.
Number 11. Find the exact value of the integral from 0 to pi of x squared cos a third x with respect to x, 6 marks. Okay, so here we have to integrate by parts, and I'm just gonna ignore the limits for now and just focus on integrating this. So here we can say let u equal, we're going to use the late technique to help us pick what u should be. So L is for your logarithms, A is for your algebra, T is for your trig, and E is for your exponential functions. So here we've got a trig function as well as algebra. So you pick whatever is higher up on the list to be u. So algebra is higher up on the list, so the x squared becomes your u. And then dv dx becomes the other function, which is cos 1/3 x. So du dx here, if you differentiate your x squared, you get 2x. If you integrate dv, you get v. And here that's integrate cos, you're going to get sine of 1/3 x. And then differentiate the inner function, you get 1/3. So divide by that 1/3. Dividing by 1/3 is the same as multiplying by 3. So now we have that the integral of x squared cos 1/3 x with respect to x is equal to, from the MF19, we know that the integral of u dv is equal to uv minus the integral of v du. So in our case, that's uv, which is 3x squared sine 1/3 x minus the integral of v du. So 2x times 3 sine 1/3 x, which is 6x sine 1/3 x with respect to x. So this part here, we still have to integrate that by parts. So let's do that. We want to integrate 6x sine 1/3 x with respect to x. Let u, again, we've got algebra and trig, so the algebra has to be the u by late. And dv dx here is sine 1/3 x. So if you differentiate 6x, you get 6. If you integrate sine 1/3 x, you get negative cosine of 1/3 x. Differentiate the inner function, that's 1/3. Dividing by 1/3 is the same as multiplying by 3. So you multiply by 3. And so this means that the integral of 6x sine 1/3 x with respect to x is equal to uv, which is 6x times negative 3 cos 1/3 x, which is negative 18x cos 1/3 x, minus the integral of v du, which is the integral of negative. In fact, I'm going to have negative, so I can just write that as plus. And that's 6 times 3, which is 18 cos 1/3 x dx. This is a lot of integration. Okay, so we go again. We integrate. This is equal to negative 18x cos a third x plus, now we want to integrate this. It's 18 sine of a third x. Differentiate the inner function. You get a third. So divide by a third, which is the same as multiplying by 3. And so if we integrate this, or rather if we simplify, because we've already integrated this, this is negative 18x cos a third x. And then I've got 18 times 3, which is 54. That's sine of a third x. And we can go back and substitute this part here with this result. And so we have that the integral of x squared cos a third x with respect to x is equal to 3x squared sine a third x minus, be careful with the negative sign, and then a big bracket, we've got negative 18x cos a third x plus 54 sine a third x. So the integral of x squared cos a third x dx is equal to 3x squared sine a third x minus minus, so plus 18x cos a third x minus 54 sine a third x. I think I'm just going to factor out a sine a third x from these two, and then we'll bring back our limits. So I've got sine, I could probably also factor a 3 out from them, but doesn't feel necessary. So sine a third x, and then we've got 3x squared here, minus the 54 there, and then plus 18x cos a third x. And now we can bring back our limits. Our limits are from 0 to pi. So let's substitute. We'll start with the upper limit. We've got sine of a third multiplied by pi. And this is multiplying 3 pi squared minus 54 plus, that's 18x, so 18 pi cos a third pi. There's a lot of brackets. Then we'll do the lower limit. Here I'm going to have sine of 0, which I know is 0. So this is 0 multiplying this bracket, so that gets 0. And then here I've got 18 times 0, which is going to make this whole part 0. So the lower limit really doesn't give us anything. Okay. So let's simplify. We've got sine of pi over 3. Make sure you are in radians. Pi over 3, that gives us root 3 over 2. And this is multiplying 3 pi squared minus 54. Then we've got plus 18 pi times cos pi over 3, which is a half. So we have that root 3 over 2 times 3 pi squared minus 54. Then 18 pi times a half, that's just 9 pi. And that there is our final answer and also the very end of the question paper. So I hope you found this breakdown useful, and if you enjoyed how I broke down this paper and you want me to assist you with your A-level math, then make sure to click the first link in the description down below, and then we can discuss how best I can assist you. Otherwise, like the video, subscribe, and I'll see you next time.